Right, we're going to move on now to talk about the specific subspace of the range. So the range is the first one we're going to look at in detail. We'll actually come back in our next lecture and look at the null space. So the range of an operator. We have an operator T. The range of T is the set of values in the output space such that there is some x in the input space, where y is equal t times x. So this is a heavy math notation here. Let me walk you through what this is saying. Y is an element in the set of the output space. Okay, that's what this is saying. So y is in the output space, and this is saying it's defined to be the set of values of y in the output space that satisfy the following properties. So this backwards looking E actually means there exists. So this is saying there exists an x. This means an element. There exists an x which is an element of the space that's the input space. Okay, so there exists x in the input space. This little backwards E means such that. There exists x in the space vi such that y is equal to tx. Okay, so this is basically saying y is in the range of t if and only if there exists an x in the input space so that y is equal to t operating on x. The vector y in the output space can only be in the range of t if there is an x that gets you there. There must have been an x in the input space that got you to something in the output space. So we also have this relationship. The range of t is equal to the range is equal to t operating on the entire input space. And so this is sometimes called the image of the input space through the function. So this is the definition for the range of an operator. So again, the range is a proper subspace of the output space. If the operator is a matrix, then the range is the span of the columns of that matrix. So here again, I'm going to assume A is a matrix, m by n. And again, here's the definition for range. It's the y in this case, it's in Rm, since our matrix A is real m by n. So instead of just having some vague input space, here our input space is Rm. And so there exists an x in the set of real n-dimensional vectors such that y is equal to a times x. Y is equal to a times x. So in this case, our input space is Rn, and for any x, it goes through this transformation. I get a y. That y is going to be in the range. The output space is Rm, so just by this definition, A is of dimension m by n. So this takes an n-dimensional vector, you multiply it by A, and you get something that's in m dimensions. Okay, so I can easily get something in a different dimension, the output space being a different dimension than the input space, just by having a matrix that's not square. So usually we often think of matrices as being square, but most matrices are not square. They're rectangular. They can either be tall and thin, or they can be short and fat. So a square matrix is actually a special case of matrices. So basically what this is saying is that for every y in the range of A, there exists an x in the input space such that y is equal to a times x. So this is the definition of the range. So stay tuned now for the practice problems where we'll look at all the different types of things we have just defined, a lot of math definitions, and we'll look at these more in detail.